So Professor Shigeki Takeuchi was not able to come since this coronavirus, so he kindly sent us his offline presentation, so you will see everything and even hear him. I would like to ask you, if you have any questions related to this lecture, just write it down and give me. And I will pass these questions to Shigeki and he will answer you. Moreover, if you want to communicate with him directly, ask me again and we arrange this meeting in proper way. Okay, so let's start. It's about 1.5 hour lecture for whole period, yeah, without question.
This is Shigeki Takeuchi from Kyoto University. Today, I would like to have a lecture on quantum sensing using entangled photons. Before starting the lecture, this is a message before lecture. Firstly, I'm sorry for that I can't give this lecture to you directly at Sochi due to the current situation of COVID-19 in Japan. I wanted to avoid any risk of the dangerous disease for the attendees of the winter school. I beg your kind understanding and sorry for the inconvenience. This is the contents of my lecture. In the first part, I would like to briefly introduce the concept of entangled photons. Second topic is an entanglement-enhanced microscope, which is a differential interference contrast microscope with a signal-to-noise ratio superior to the standard quantum limit. The third topic is about ultra-high resolution quantum OCT with a very big merit that group velocity dispersion tolerance. The fourth topic is infrared quantum absorption spectroscopy. Then I would like to conclude this lecture. So let me start with the concept of quantum entanglement. Quantum entanglement is the superposition of different states of the correlated particles. I will let you know later in more detail. The quantum state of each particle cannot be described independently. This is an example of the entangled particles or entangled photons. We can make such kind of state using spontaneous parametric down conversion. Is depicted here. When you put our ultraviolet laser beam into a nonlinear crystal, in this case beta varying borate, then with some appropriate phase matching condition, you can generate a pair of photons into two directions with satisfying energy conservation law and momentum conservation law. In this case, horizontal polarization photons are generated into this direction, and vertically polarized photons are generated into this direction. However, when you select these two crossing sections, then maybe the photon has a horizontal polarization. In that case, the other photon has the vertical polarization and vice versa. So if we name the photon emitted into this direction photon A and this direction photon B, we will have a coherent superposition of these two cases. Photon A has vertical polarization, and photon B has horizontal polarization, or vice versa. In this case, when you detect these two photons with some polarization measurement setup, in this case, the setup can distinguish vertically polarized photons and horizontally polarized photons. Then the results are like this. So when you detect photon A in vertical polarization, photon B is found to be horizontal. When photon A is horizontally polarized, photon B is vertically polarized, and vice versa. So you will observe perfect anti-correlation in these two measurement results. However, there is a bit interesting point. Due to the coherence, the same state of photons can be written in the different form. As you may know, a vertically polarized photon is in a superposition of diagonally polarized photons and anti-diagonally polarized photons. Therefore, the same state can be written in this form. In this case, the state is a superposition of these two cases. The first case is photon A has diagonal polarization and photon B has anti-diagonal polarization. And the second case is photon A is anti-diagonally polarized and photon B is diagonally polarized. Therefore, when you measure this state with a different measurement setup, it means when you perform the measurement in diagonally polarized measurement bases, photon A could be found in diagonal polarization. In that case, because the state is written here, photon B will be found in anti-diagonal, and so on. So you will find perfect anti-correlation in this diagonal polarization basis. And this is a bit curious because perfect anti-correlation in different measurement basis set should never happen in. It's a big debate between Einstein and Bohr. So does quantum entanglement exist? So Einstein wrote this paper and published in Physical Review. Can quantum mechanical description of physical reality be considered complete? And he suggested, he and his co-authors suggested that maybe the description of reality given by the wave function in quantum mechanics is not complete, or digit quantities cannot have simultaneous reality. And Niels Bohr wrote a paper exactly with the same title, Can Quantum Mechanical Description of Physical Reality be Considered Complete? And fired back. At that time, entanglement is a kind of philosophical issue. However, now entanglement is a useful resource for many interesting tasks. In the former explanation, I used entangled state in polarization, but even photons can be entangled in many other degree of freedom. For example, frequency or color or photon number or even angular momentum of photons. And those entangled states can be used for quantum communication or quantum computation or even quantum metrology or quantum sensing. And one important thing is that for these applications, we have to develop specific entangled states of photons. So applications require different types of entanglement. This is a famous example of the entanglement over 140 km. So in this experiment, one of the entanglement photons is delivered over 140 km using telescope, and they confirmed entanglement between these two distant parties. This is our work. If entangled photons can be generated even using a photonic quantum circuit. In my talk, I will not explain the details, unfortunately. However, we developed an entanglement filter. So when you inject two diagonally polarized photons into this photonic quantum circuit, then because this photonic quantum circuit extracts the cases where these two photons have either vertical polarization or horizontal polarization. Therefore, the result will be an entangled state of these two cases. So let me move to the next topic, an entanglement enhanced microscope. Optical phase measurement is widely used in various fields of science, including gravity wave detection and gyroscope, and also cosmology. In the case of gravity wave detection, very large optical interferometer is used for gravity wave detection. And in case of gyroscope, this is laser gyroscope, Sonic type interferometer is used to detect angular velocity. And in case of cosmology, here four telescopes are connected by actual optical interferometers to increase. There are two concepts about optical phase measurement. One is sensitivity and the other is precision. There is no limitation for better precision. Using larger number of photons, you can get better precision at will. However, there exists a limitation for sensitivity. Here, sensitivity is a precision divided by the number of photons used to measure the optical phase. So this is one example, the usage of sensitivity. As you may know, super sensitive film can work with. Before going to the details about the sensitivity, I would like to introduce the concept phase super resolution. Here we assume that some sort of quantum state of photons in two optical modes is input to the system, and this is the phase shifter phi, and the state is converted or interfere at the beam splitter, and the outputs are detected by detectors. When we use classical light or single photons as input, we will observe a kind of output with fringe period of 2 pi. So here we observe some sort of destructive interference, so the output is 0, and then become maximum at phase pi, and then return to the 0 when pi equal to pi. However, when you put different type of quantum state, entangled state, the situation is totally different. This is the case when we input so-called two-photon null state. Null state is a superposition of two different cases. The first case is n photon is one mode and 0 photon is in the other mode, and vice versa. And when this is a kind of entangled state. And when you input this state, this is sometimes called null state, into this interferometer and perform coincidence detection as the output. So what you will observe is this sort of fringe with a period of pi. And this behavior have been already experimentally demonstrated for n equals 3 and n equals 4. And people thought that maybe this is a kind of unique phenomenon. In 2007, Lesch demonstrated phase super resolution with coherent light, or classical field, and post selection. And here is a very big question: what's the difference between classical and quantum states for such kind of super resolution? Actually, for such kind of question, the concept phase supersensitivity was introduced. The question is, with a given number of photons, how much is the minimum uncertainty for the phase? For classical light and single photons, the minimum uncertainty for the phase is given by 1 over square root n. This is called the standard quantum limit or short noise limit. As you may know, when you increase the number of experiments, for example, if you take a data and if you perform the same experiment, for example, 10 times more, in that case, the standard deviation is reduced by 1 over square root 10. So the concept is the same with such kind of reduction of deviation. And in the case of null state, for example, n equal to is shown here again. In this case, when you use quantum state, entangled state, psi, as a null state, in that case, the minimum uncertainty for the phase is given by 1 over n. And this is called the Heisenberg limit. This is because in the case of classical light, in order to measure the change in phase, maybe you put a sort of bias phase here and try to observe the change in phase by monitoring the output here. So this maximum slope is a kind of gives you the sensitivity. However, in case of null state, because the fringe period is half of this classical case for the case n equal to. Therefore, this slope is twice as large as this guy. However, because the number of photons used here is twice of this one, so as a result, the difference is given by square root 1 over square root n. So, quantum metrology is towards the ultimate sensitivity using entangled photons. As I have explained, operation with n photons can be improved from 1 over square root n to 1 over n in an ultimate limit. I mean, maybe to reach this limit is quite difficult and maybe impossible. However, I would like to say is there is plenty of room for improvement. And in an ultimate limit, when you use 1 joule of laser power, the same precision could be achieved just using 1 nanojoule of laser power. So such a measurement could be very useful for faint light probe is necessary. So maybe this sort of technique could be used for biological applications. Some years ago, we performed this experiment, beating the standard quantum limit with 4 entangled photons. In this experiment, we generated a kind of 4-photon Moon state. Here, 4 photons is generated in one spatial temporal mode, and this 4-photon state is in a superposition of rotating in clockwise direction and counterclockwise direction in this displayed Sagnac interferometer, and we performed coincidence detection using several single photon counting modules, and these are results. So this is a case where single photon input is used as input state, so phase is from 0 to pi and 2 pi here. And this is a case 2-photon Fock state is used as input, and this is the case when 4-photon input is used. And the visibility of the fringe for this 4-photon Moon state interference is 91%, and this value is larger than the threshold visibility of 81.6% to beat the standard quantum limit. Actually, because using such kind of quantum interferometer, one could beat the standard quantum limit for optical phase measurement. So some people are interested in our work. For example, Scientific American selected our result as one of the best achievement in that year, 2007. But we also received some opinion or criticism, like it sounds nice, but how can we make use of it? In order to answer such questions, we demonstrated an entanglement-enhanced microscope. Differential contrast microscope is an optical microscopy illumination technique used to enhance the contrast in unstained, transparent samples. DIC works on the principle of interferometry to gain information about the optical path length of the sample to see otherwise invisible features. And this DIC has been used in many areas, including life science. It is because unstained biological samples can be observed, and furthermore, this DIC can sense the change in refractive index. It means that sensing of the small change in density, volume, chemical contents can also be performed. This is one application of LCM-DIM, differential interference contrast microscope. In this experiment, interestingly, a unit step on ice crystal surfaces has been directly observed, as is shown here. Please note that they observed the formation of ice crystal in water. It means that they can sense the very small change of refractive index between ice crystals and water was detected with a monolayer depth resolution. And in such experiments, signal-to-noise ratio determines the depth resolution limit of LCM-DIM. And this is the schematic of LCM-DIM. When the laser light, in this case laser light, is input to the polarizer, and then the polarization is divided into the two optical passes using our special prism, and blue line indicates the vertical polarization path, and red line indicates the horizontal polarization path. And then these two optical beams with different polarization is focused on the sample with slightly different spot, as shown like this. Okay. And then these two optical path components are recombined using another prism, and then detection is performed. And the sample is scanned as is shown here with the two laser spots. And because the output is reflecting the difference of the optical path lengths, so at this point, because blue is focused here and red is focused here, so there is a sort of change of the optical path between the two optical beams. Therefore, the count increases at this point. But again, on the top of the surface, the two optical paths are the same, so the detected count returns to the original bias point. And at the opposite side, the opposite happens, so you will observe the decrease in the detected counts. And with these two signals, you can say that there is a sort of point that optical path length is larger than others, and you can make a kind of image using this sort of data. And for a limited probe light intensity, note that this is numerical simulation. So you observe a kind of shot noise due to the limited amount of probe light intensity. according to the Poissonian distribution. And when the probe light intensity is decreased for faint probe light, the noise part is increased according to the signal level, right? And here this is a signal, but the noise due to quantum nature of light equals to the signal amplitude. This is so-called the standard quantum limit. This is the case we assume 1400 photons. When probe light is further weakened, 140 photons, now signal is no more recognizable from the shot noise. Then this is the concept we proposed and demonstrated, entanglement enhanced microscope. Instead of laser light beam, we use noon state source here, and the detection part is replaced by coincidence detector. And in this case, because we put noon state onto the sample, as we have learned before, the fringe period is half in case n equal to noon state. And in this case, the signal is given by this equation, and noise is also this equation. So signal to noise ratio can be calculated using this formula, and so this is given by 1 over delta phi, and so quantum signal to noise ratio is n given by n times delta phi, and classical signal to noise ratio is square root n times delta phi. So when you compare this factor and this factor, SNR can be improved by a factor of square root n. So this is a kind of numerical simulation with entangled photons and with classical light. For a given light intensity or given photon number, the level of background is half of that with classical light in case of entangled photons. And please note that the vertical axis is detection events. So for classical light, this is a single photon click, and for entangled photons, this is the number of coincidence events. And when you consider, for these two cases, we assume 1400 photons are used for this measurement. But because of the change of the background level, so shot noise is larger for classical case. So when you compare these two cases, contrast is improved because signal height is the same, but background level is half. And when we assume that we could realize noon state interferometer with n equal 10 with a given number of photons, 1400, contrast is greatly improved, as is shown here. This is the experimental setup we used to demonstrate entanglement enhanced microscope. This part generates entangled state in polarization, and that is divided into two optical passes using calcite crystal, and then focused to the sample, and then recombined by another calcite crystal. And this is a coincidence counter. And this part corresponds to the differential interference microscope. And instead of using this sort of proof of principle setup, we could use normally used differential interference microscope setup. And for this part, we generated a kind of polarization entangled state, as shown here, and fidelity is 98%. And at the point of the sample, the two beams are focused into these two adjacent spots. And this is a real experimental setup we used. And please note that this is the entangled-photon source, and the generated entangled photons are guided into this DICM setup using optical fiber. And we checked our interference fringe visibilities. So this is a case for single photon interference. Visibility was 97%, and this is a fringe for two photon interference, n equal to null state, and visibility was 95%. And from these two data, when you look at this paper, there are some sort of optimal bias point, and we selected bias phases to obtain the maximum signal to noise ratio. For a sample, a glass plate sample on whose surface a Q shape is carved in relief with an ultra thin step using optical lithography. So the step here is 17.3 nanometer. This was measured using atomic force microscope. It's about 100 atoms. And please also note that we are not exactly sure what is the real step. This is a measurement result by AFM, but as you observe, there are some sort of deviation. And the size of Q shape is 500 micron. And the glass plate is BKSM glass, refractive index about 1.5. And we scanned the two focal spots like this. And this is the result, 2D imaging using entanglement microscope. So this is the case using single photon interference and single photon detection. And note that average total photon number detected was 920 photon per pixel for each pixel. And the pixel size is 20 micron times 20 micron. And this is the case when we used two photon null state and coincidence detection. And the number of detected counts is 920, the same. So as you observe using these two figures, this quantum image has a better contrast. And in order to verify the improvement of signal to noise ratio quantitatively, we checked the raw data of this section. And this is a comparison of signal to noise ratio for a section of the image. And this is the case of raw data of classical image, and this is again raw data of quantum image. And from these two data, we can calculate signal and noise factor. And in this case, SNR was 1.58, and this quantum image has SNR 2.13. And the ratio between these two images is 1.35. For n equal to noon state, the maximum improvement could be square root 2. It means 1.44. However, this is slightly smaller than that maximum amount, 1.44. It is mainly because the two focal spot, Gaussian spot is slightly overlapping together, and the visibility of the single photon interference and two photon interference is not 100%. When we take these two points into account, our theory suggests the SNR ratio should be 1.35. So this experimental value is almost the same with the theory value. So improvement of SNR has been demonstrated. And from these two data, we can estimate also the thickness of the Q-shape figure. And the estimation by AFM was 17.3. And from classical image, this height was estimated about 16.6 plus minus 1.1 nanometer. And for this one, 17.0 plus minus 0.9 nanometer. Here, the important point is not these two values, but these two errors. So when you compare 1.1 nanometer and 0.9 nanometer, we can confirm entanglement enhanced microscope can estimate the step height with better precision for the given probe intensity. So this is a short summary about the noon state entanglement enhanced microscope. When we could increase the number n of noon state, we can have better contrast. So, for example, for n equal 4, sensitivity could be improved by factor of 2, and for n equal 10, sensitivity could be increased to 3.3. But in this case, please note that for the same signal to noise ratio, the intensity of probe light, probe beam can be reduced by 1 decade. So application for the detection of small change in living cell or formation protein crystals could be monitored effectively using such kind of entanglement enhanced microscope. Next, I would like to move to the third topic, toward ultra-high resolution quantum optical coherence tomography. This technique uses the first I would like to introduce the concept monocycle entangled photons proposed by Professor Steve Harris in Stanford. Monocycle entangled photons is a state where two photons are created in a very short time, a few femtoseconds, only one cycle of light oscillation. If we could generate such an entangled state of photons, there are many interesting applications. The first one is quantum optical coherence tomography. The second one is giant two-photon absorption. And the third one is clock synchronization. And we can enjoy super resolved quantum optical coherence tomography and largely enhanced to photon absorption and super precise clock synchronization. So this is to explain the concept of monocycle entangled photons. When you have a weak CW laser light, maybe you could have single photons at random in time, as shown here. And when you use attenuated monocycle pulse lasers, in this case, you might able to have 2 photons in a very short timing within a few femtoseconds. However, the number of photons in a pulse is not determined. The photon number distribution follows Poissonian distribution, so sometimes 2, but sometimes 1, and sometimes 0, even when the average is 2 photons in a pulse. And this is the case of monocycle entangled photons. As shown here, 2 photons are always found at the same time in a few femtoseconds, but the 2 photons are at random in time. Another important thing is that when you look these figures carefully, maybe you can recognize that the colors, this one is from red to blue, and this one is from blue to red. So, but in this case, the colors are both from blue to red. So there are some differences. In this case, the total sum energy is exactly the same and determined. That is another critical difference between monocycle entangled photons and photons in attenuated monocycle laser pulses. And in order to realize such a monocycle entangled photon states, it means the correlation time window is very narrow. And these are 2 photon wave function. Amplitude of 2 photon wave functions are plotted like this. And this is appropriate for in terms of frequency, and this is in terms of time. So monocycle entangled photon has the very strict correlation in frequency. And when you perform 2-dimensional Fourier transform, that is converted into this plot. And this means that when you find 1 photon, signal photon at one time, the ideal photon is found exactly at the same time, and in any cases, right? And the temporal width is given like this. And in order to have a small temporal width due to the Fourier transform, you need a very large bandwidth in frequency. So delta t is given by 2 pi over delta omega. So to realize monocycle entangled photons, the bandwidth delta omega should be very broad, comparable to the center frequency omega c. And this is how to generate such kind of broadband frequency entangled photonic states. In this case, we used magnesium doped stoichiometric lithium tantalate, and we created chapped quasi-phase matched device. QPM is for quasi-phase matching, and in this case, this period, polling period is 8 micron, and the another end is 8.825 micron. So at each section, our phase matching condition is different. So at each part, different type of photons are generated but the some frequency is exactly same with this pump frequency, according to the wavelength of 532 nanometer. And this is the result of the parameter fluorescence generated from the device I explained. This data was measured by superconducting nanowire single photon detector, and this one is measured using photomultiplier tubes. And for these, we take the same data using two different type of detectors. And in both cases, ultra broadband parameter fluorescence was observed for non-collinear condition. In this case, we generated photon pairs signal and idler into two different directions. And when we calculate the correlation time using this bandwidth, maybe theoretically calculated some frequency generation signal is 4 femtosecond in time. It corresponds to 1.1 cycle. And we are able to use such a broadband frequency entangled photons for different applications. And the target application here is quantum optical coherence tomography. And it is now often called OCT. And OCT is using low coherence interference, and the current and this technology is used for example, observing the intersection of eyes. This is the part of retina, and this is the intersection of retina, and doctors can detect some disease by looking at these images. And now depth resolution of OCT is limited around 5 micron to 10 micron. But when we replace the low coherence interference used to optical coherence tomography to two photon interference using frequency entangled photon pairs, as I will explain later, depth resolution of quantum optical coherence tomography would be below 1 micron. And I will explain why we could expect such kind of things later. So here I would like to explain why we have such kind of limitation for optical coherence tomography. So because optical coherence tomography is using low coherence tomography, low coherence interference, this low coherence interference signal FWHM increases due to dispersion in media. Chromatic dispersion is that when you have blue light propagating in water, the speed of blue light is slower than red light. So the speed of light changes according to its frequency. That is called chromatic dispersion. And therefore, maybe you can imagine that due to such kind of dispersion, this low coherence interference signals is broadened. And in case of low coherence interference, if you increase the bandwidth of the low coherence light, then in principle, due to the Fourier transform function, resolution can be increased. So according to this blue line, this is a case where we don't have any dispersion material with dispersion, blue line. However, normal medium has some sort of chromatic dispersion, and if we have some dispersion, when we increase the bandwidth of the low coherence light, due to the chromatic dispersion, the signal width increase dramatically. So there is a sort of optimal point that was around 10 micron or something like that. And actually, some years ago, it was already known that quantum optical coherence tomography's resolution is better than optical coherence tomography for the same bandwidth of the source. However, at that time, improvement factors differed in reports. Square root 2 or 2 was under debate. And the second point is that even the chromatic dispersion cancellation was expected for quantum OCT. However, dispersion cancellation has been demonstrated just in low resolution 2 micron cases. Before talking about the details about quantum optical coherence tomography, here I would like to introduce the concept two-photon quantum interference, or people are using the scientists who found this phenomenon, Horn-Mandel interference. When you have two single photons and when you inject two photons simultaneously into a beam splitter, 50-50 beam splitter, you may have these four cases. The first one is the left one is reflected and the right one is passing through the beam splitter, and the second case is the vice versa. And the third case, both photons are reflected. And the fourth case is that both photons transmit the beam splitter. And when for classical particles, definitely we have these four scenarios, four cases, four processes. However, in the case of quantum mechanics, if we have the same initial state, actually these four cases are identical initial state when these two photons are indistinguishable. And if the final states are also not distinguishable, the process may interfere. So when you look at these four cases, among four, this case and this case has exactly the same initial state and final state. Therefore, these two processes can interfere. And in that case, what you need to do is you have to calculate probability amplitude of these two processes, and first you need to sum up these probability amplitudes, and then when it is squared, you can find the probability. And interestingly, this process and this process has the same probability amplitude, but the sign is opposite. Therefore, these two processes destructively interfere, and we cannot find these two cases. So, in short, when you put two photons simultaneously into a beam splitter, what you will observe is just these two cases. Two photons are found in the left output port or right output port. This is called Horn-Mandel interference. And it was also found by Steinberg, Kwiat, and Chow in 1992. when we use frequency entangled photons as our input, two photon interferinges are not affected by group velocity or even order dispersion. So this is a kind of schematic to explain why group velocity dispersion is cancelled for such kind of home-boundary interference when we use frequency entangled photon pairs. So this is the source for frequency entangled photon pairs, and this is the pump, and now blue photon and red photon and middle photon is the center, and blue and red are generated. And suppose blue is passing through the idler path, and red is for signal path, and there is some sort of medium with chromatic dispersion. And in this case, because the speed of light for red photon is larger than that of green photon, so red photon is going ahead. Now, the position of green photon is considered as a sort of standard. So at the beam splitter, because of this chromatic dispersion, red photon is coming a little bit faster than blue. And when we consider the case both of the photons transmit the beam splitter, so you may have this sort of condition. However, we can also consider this case. Now, in the idler path, red photon is propagating, and blue photon is in signal. And in this case, when we compare the speed between green photon and blue photon is slower, so we will have this sort of situation. And opposite to the above case, we now consider the case both photons are reflected. And when you look at these two final states, interestingly, these two final states is exactly the same. And also, because these two cases are superposition, I mean, we are talking about the frequency entangled state, so these two processes are coherently superposed. Therefore, we are not able to distinguish these two cases neither. So, as a result, these two processes cannot be distinguished and destructively interfere. So, I mean, even when we have chromatic dispersion, we will observe the two photon interference at the same condition. So we don't see any change due to the chromatic dispersion. And this is the experiment setup we used to test some properties. For example, the bandwidth and dispersion cancellation. And in this case, we used BBO type 1 crystal and generated broadband entangled photons with the bandwidth of 80 nanometer. And we have also found that for the same bandwidth of photons, when the spectrum shape is rectangular, actually resolution increment factor is 2. However, if the shape is Gaussian, improvement factor is square root 2. So as I mentioned in the former study, in some paper, factor was considered 2, or in another paper, factor was square root 2, but in reality, enhancement factor depends on the spectrum shape. And actually, we have found that this is not neither rectangular or Gaussian. It's a kind of intermediate shape. And for this case, we observed the resolution increment factor of 1.65 for these two classical low coherence interference and this Horn-Mandel quantum interference. And when we take this intermediate shape into account, our theoretical calculation suggests the event factor should be 1.69. So we have confirmed that spectral shape matters for resolution enhancement. Another bit interesting point is that if we could have perfect dispersion cancellation for any pump beam for the generation of entangled photons, and the answer is no. In order to have a perfect dispersion cancellation, we have found that the pump line width should be very narrow. Actually, this effect was discussed in this former paper we found later. And this is our experimental demonstration. We used very small line width pump light with 100 kHz line width. And this is almost negligible for this sort of experiment. And this is a case of optical coherence tomography, 4.2 micron, and classical case, classical OCT. But when we put dispersing material, water of 25 millimeter thick, then this signal is changed into this one, so the resolution is degraded a lot. 9 times. But in case of quantum OCT, this is resolution is 3.0 micron, and even with this dispersion material, water, we don't see any change in the resolution of Horn-Mandel dip without any degradation. So, as far as we know, this is the first experiment dispersion cancellation is demonstrated in high resolution regime. And in order to improve the resolution, we constructed novel source ultra broadband parameter fluorescence at visible to near infrared region. And in this case, center frequency is 800 nanometer, and the bandwidth is from 660 to 1030 nanometer, covering all the so-called transmittive window of water. Maybe this sort of source is suitable for ophthalmology. And for this source, we used 6.7% sharp quasi phase matched device. The device was periodical poured crystal. Again, stoichiometric lithium tantalate was used. And this is a numerical simulation for this chapter device, and this is the experimentally observed spectrum. And we also performed Horn-Mandel interference experiment using the source I have shown. So this is the case quantum OCT, and this is OCT. It's a bit opposite to the former one. So this is the case when we don't insert any dispersive medium. So the resolution was 0.54 micron. And when we use one of the parameter fluorescence as a source of broadband single photon, we can perform classical optical coherence tomography. And in that case, low coherence interference signal showed 1.5 micron resolution. And now we insert just 1 millimeter thick water onto the path of the signal photon. We don't see almost any changes. Slightly increased, however, within the error bar. But in the case of optical coherence tomography, resolution is degraded drastically. So, home and dip corresponding to 0.54 micron resolution quantum OCT is achieved, surpassing 0.75 micron. This is a record of classical OCT for 20 years. But more importantly, we demonstrated dispersion tolerance of quantum OCT for this extremely high resolution region. That is, I think, the important message of this experiment. And we also made a sort of two-dimensional image. And for this experiment, we used moderate resolution of 3 micron depth resolution. And this is a case without dispersion of classical OCT and quantum OCT. But when we use some sort of dispersive material, this is zinc sulfur material is inserted, whose dispersion is corresponding to 40 millimeter thick water. So the image was totally degraded. But for quantum OCT, we don't see almost any difference. And these are resolutions. No degradation is observed with dispersion medium. Next, I would like to move to the final topic, infrared quantum absorption spectroscopy. Infrared absorption spectroscopy is now widely used in many areas of science. It is because molecular recognition is possible using the infrared absorption spectrum, as is shown here. This is borrowed from JASC homepage and now used in labs of chemistry, pharmacy, or life science. And also, this sort of absorption spectrometers are used for production monitoring in chemical plants. In this lecture, now I define my mid-infrared is from about 2 micron to 5 micron, and far infrared is 5 micron. There is a problem with current infrared absorption spectrometers. And this is one example of infrared Fourier transform spectrometer. And this is a schematic of the spectrometer. And here is a light source, and here is a detector. And this is a kind of interferometer. And this is sample room. And the light source Normally, lamps or very hot heaters uh, are used, and those light sources are with low energy conversion efficiency. And it's also difficult to make the source or surrounding setup compact because normally the light source is very hot. And about detectors, if you'd like to have a very high sensitivity, liquid nitrogen cooled detectors are required. For these reasons, uh, it is difficult to make small and cost reduced and higher sensitive spectrometers using current technology. Infrared quantum absorption spectroscopy is a novel idea. It enables using a visible light source and the detector, infrared absorption spectroscopy is possible. And now, the evolution and cost reduction of visible light detectors and sources are remarkable. So maybe we could expect significant downsizing with high sensitivity. For example, current spectrometers could be replaced by smaller IRQS devices, and on-site analysis may become possible for environmental study or some other activities. This is the principle of IR quantum absorption spectroscopy. One interesting point is that, again, frequency entangled-photon pairs are used for this technology, but now we use two sets of crystals. And interestingly, there may be the case photon pairs are generated in the first nonlinear crystal, or the photon pairs may be generated in this nonlinear crystal too. And as the photon pair generation process in the first and second crystals interfere quantum mechanically, entangled-photon pair generated is suppressed or increased. So when we are not able to determine where photon pairs are generated, either non-crystal 1 or nonlinear crystal 2, in that case, these two processes interfere. And as a result of interference, the amount of photon pairs generated fluctuates due to the interference of these two processes. But suppose, for example, in this case, these two processes destructively interfere and we don't see any signal light. But when you put absorber of infrared light here, the quantum interference between the two crystals are interfered and collapsed due to IR photon absorption. And as a result, in this case, we don't see any visible light at this spot, but as a result of collapse of quantum interference, signal light can be detected. This is the reason why we can sense the absorption in infrared region just using signal light detector, visible light detectors. So this is the first demonstration, as far as I know, about the infrared quantum absorption spectroscopy by the group of Singapore. So in this case, they used two nonlinear crystals, and the visible photons at 580 to 620 was generated with the infrared photons at around the wavelengths of 4.2 microns. and this is the fringes corresponding to the constructive and destructive interference of the two processes. And when you look at the fringes, this is the case where nothing is inserted between the two crystals, and this is the case where carbon dioxide gas is inserted, filled between the two crystals. And you can observe the degradation of visibility in this case. So with this degradation, IR absorption due to carbon dioxide is estimated. So this is a very nice experiment. So this is a summary of my talk on entanglement enhanced microscope and ultra-high resolution quantum OCT, and briefly infrared quantum absorption spectroscopy was introduced as examples of quantum sensing using entangled photons. And actually, this is me, and this is my group member this year. And I would like to thank my collaborators shown here, and also funding agencies. And finally, I would like to briefly introduce our group and Kyoto University. And this is a map of Kyoto. And Kyoto is a charming and a little bit compact city. And for example, this is the famous Golden Temple, but there are many other lots of sightseeing spots and historical architectures here. And Kyoto University is the main campus is here, east side of Kyoto, east side of Kyoto, and our campus, Katsura campus, is sitting in the west side. And in my group, we are working on, this is our motto, juggling with photons at will like otedama. In Japan, children play with these small, tiny beanbags, like this, juggling. And we'd like to be a photon juggler. And our group is working on photonic quantum circuits and photonic quantum metrology issues, and also nanophotonics for quantum information. And about nanophotonics works, for example, we are making efficient single photon source using diamond NB center nanocrystals coupled to our tapered optical fibers, and as this device generated about 7 times 10 to the 5 single photons emitted through single mode of optical fiber. That is the most efficient, one of the most efficient source of diamond NB centers. And we are also making nanofiber black cavity. The purpose is using partial enhancement. Maybe we could efficiently couple all the photons emitted from single light emitter into single mode optical fiber. And we have successfully demonstrated coupling single quantum dot onto this very tiny nano cavity embedded in nano tapered optical fiber. Okay, thank you very much for your kind attention, and I hope you could sometime visit us in Kyoto, and especially we are soon expecting spring, and you can enjoy very beautiful cherry blossoms. And this is the message after the lecture. I hope the whole lecture was somehow beneficial for you. And if you have any questions, please send an email to takeuchi@kyoto.com. KUEE Kyoto University, Kyoto-U AC.jp. And I wish the situation about COVID-19 is getting better soon in the world, and hope to see you sometime later soon. Thank you very much for your kind attention. Bye bye.
Okay, so let me